Hey guys, welcome back to General Chemistry. Today we're going to dive a little bit deeper into these covalent bonds. So up until this point, we know electrons are shared. And then we also are starting to see these molecules in 3 dimensions. But now we want to talk a little bit more about how exactly are these shared. So let's observe the following molecule. So here we've got hydrofluoric acid. So in this first picture here, our hydrofluoric acid is just kind of floating around without really a care in the world. No big deal, just floating around. Okay. In this second picture, what we've introduced are electric fields. So over here, we've got a negatively charged electrode. Over here, we have a positively charged electrode. So what we've done in this picture is we've gone ahead and turned on those electrodes. So there's an electrical signal going through those. And then what we see is instead of these molecules kind of floating around randomly, we see these molecules all of a sudden line up very distinctly. So for these hydrofluoric acid, the hydrogen is the white, the fluorine is the green. So what we see is all of the hydrogens all of a sudden face the negatively charged electrode, and all of the fluorines face the positively charged electrode. So really the only explanation for these molecules to go from like floating around randomly to very specifically lined up is there must be some sort of charge going on between these two atoms. So how do we have a covalently bound molecule, electrons being shared, and we have the opportunity for there to be charged portions of the molecule? We got a little bit to talk about now. Okay. So all of this has to do with something called electronegativity. So electronegativity is defined as the ability to attract electrons to oneself. So while these electrons are in fact being shared between the two atoms, based on electronegativity, somebody may not be sharing them evenly. Somebody may be making themselves very attractive to those electrons, in which case they're kind of hogging them. It's an unequal sharing. So here is the electronegativity chart. So these are arbitrary numbers given by Linus Pauling. So he started with the most electronegative atom, which is fluorine up here in the top corner. And he gave that basically a 4. And then he ranked everything else based or from that. So it goes from 4, that's the highest number, all the way down to almost 0. So electronegativity, while it's an arbitrary number, just kind of randomly got assigned, these electronegativities tell us how attractive an element is to electrons. So somebody that is more attractive is going to attract or hog or unevenly share. Somebody that's less attractive is going to be left without them. They're not going to have as much of that electron near it. Well, this sets up something called a dipole moment. So if I have two atoms that are sharing electrons, so they're in a covalent bond, and somebody is really, really attractive to those electrons, somebody else is not so much, what we're going to see is those electrons are going to be attracted to one of the elements and not so attracted to the other element. And the important thing to remember here is electrons are charged particles. So if an electron is attracted more so to one side of this bond, with that electron is going to go that negative charge. So here's where we see that separation of charge. When we have this separation of charge, when there is this kind of attraction or hogging of the electrons, we call that a dipole moment, a separation of charge within a bond. Okay? Complex stuff. Let me give you an analogy that maybe will help out with this. Okay? So here I see two atoms. I've got my oxygen atom over here on the left, I've got my hydrogen atom over here on the right. So 2 different atoms. I'll tell you in this case that oxygen has a higher electronegativity. So he does a better job of attracting electrons. And I'll tell you that hydrogen has a lower electronegativity. He's not as attractive. Okay. So here's the analogy. Big brother, little brother. I have 2 boys. One is 7 and one is 5. So let's say we get a new toy, right? We get a new video game, or we get a new basketball, or we get a new bat, something like that. And they're so excited. And I say, oh my goodness, guys, I'm so happy for you. Go share this video game. Run upstairs, play your video, and make sure you guys share, take turns on it. They run upstairs. Are they going to share the video game? Well, yeah, they're going to share it. They're each going to have a turn. Are they going to spend equal time with that video game or that new bat? No. Big brother's going to hog it, right? So big brother's going to spend more time on that video game. Little brother is not going to have as much time on the video game. There's going to be a separation in the amount of time that they have with it, right? So oxygen in this case is big brother. Are they sharing the electrons? Well, technically, yes. They both have some claim to the electrons. But oxygen is hogging those electrons. So most of that electron density is over towards the oxygen side. And remember, with that comes a negative charge. Electrons are negatively charged. So we see what's called a partial negative on the oxygen side of this bond. And we depict that as such. So it's kind of a squiggly D and then a negative sign. And then little brother is left in the absence of those electrons, so he doesn't have as much time with them. So little brother, if he's left in the absence of electrons, that's going to give him that partial positive charge. Okay? So this separation, this uneven sharing, is what we call a dipole moment. And this is just another picture of the same thing. So this is hydrogen, this is oxygen. We see electron poor area over here. So the purples and blues say that I am without electrons. And then we see an electron rich area over on this side. So the oranges and reds say that I have a lot of that electron. And we call this a dipole moment. Well, how do we know if there is enough separation to denote a positive and a negative charge? Okay, so how do we know who's big brother? How do we know who's little brother? And then how do we know if they're sharing evenly or not? Well, we're going to look at their electronegativities. So we're going to take the electronegativities within a bond, and we're going to subtract their electronegativities. So if we look at the example that we were just looking at, so we had the oxygen-hydrogen bond. I'm going to take the electronegativity of oxygen, which is 3.44. I'm going to take the electronegativity of hydrogen, which is 2.20. And I'm going to subtract them. Okay, so 4, 2. So the difference in electronegativity between those two is 1.24. So that's the first step. Let's look at what the electronegativity difference is. Okay. Well, then how do we know if that's a big electronegativity difference or a small? Well, we've got this chart. If I subtract the electronegativities and that difference is 0 to 0.4, we would say, yeah, that's not really that big of a difference. So if the electronegativity difference is 0 to 0.4, we would say, they're sharing them equally. That is a pure covalent bond. No separation of charge. We're sharing evenly. If the electronegativity difference is between 0.4 and 2.0, we would say, yeah, that's an unequal sharing. There's a big brother, there's a little brother. Somebody's going to hog the electrons. So this we would call a polar covalent bond. So polar in that there is a separation of charge, covalent in that, well, technically they're still sharing the electrons. Okay. So when we did the electronegativity difference for oxygen and hydrogen, it fell about here, 1.24. So we would call that a polar covalent bond. So that's the basics of determining dipole moments. I would say practice a few of these. And then the next step that we're going to take is looking at a dipole moment and then deciding if the molecule as a whole is polar. So step one is there a dipole moment? And then step two, we'll look at the molecule as a whole. I hope you guys found this helpful.